Hello everyone and welcome back. Today we're going to continue our exploration of random variable theory for statistics and probability and introduce and talk about some theoretical aspects associated to four very important probability density functions known as the z, t, chi-square, and f distributions, which you're definitely going to see a lot once we start talking about hypothesis testing in a little bit more detail. So before we get into the main topic of today, I just want to talk about some very important things that you definitely should already know up to this point. So firstly, let us suppose that x1, x2 down to say xn, where n is finite, are independent and identically distributed random variables with each of these xk's associated to a normal distribution with some mean mu and some variance sigma squared. Then the following properties hold in terms of the relationship between these variables. One, the mean random variable of these random variables, i.e. defined to be 1 over n times x1 plus x2 all the way down to, say, xn, i.e. the average of those random variables, will also be normal with a mean and a standard deviation, so you should be able to show that the expected value of x bar is actually equal to the same thing as the expected value of each of those xk's, which is actually equal to mu x, and the variance of x bar is actually equal to the variance of each of those x variables divided by n. And some people will also write the standard deviation of x bar to be equal to sigma of x divided by the square root of m. Right? And the second property is because not necessarily if these variables are normal, so if these xk's are identically distributed and independent, non-normal random variables, then x bar will be approximately normal for n arbitrarily large. Some people will use the rule that n is bigger than 30 is sufficiently large, but that's not actually theoretically true, right? Because if you have 5 million people and you just do sample sizes of 30, that distribution is not going to be anywhere near normal, especially if the original distribution is highly skewed, right? So technically speaking, n has to be arbitrarily large, and that arbitrarily large is subjective to the population n study that you're working with. So generally, forget that whole entire n is equal to n bigger than 30 rule. Theoretically, that has no context. Now, let us define a new random variable. Let's call this random variable z to be equal to random variable x minus the mean of that variable divided by the standard deviation of that variable. So obviously x is a random variable, mu x is a number, sigma x is a number. That means z is going to be a random variable. So what type of distribution will z have, and what type of properties will z have? So we can actually rewrite this expression instead as 1 divided by sigma x times that random variable x minus mu x divided by sigma x. Right, so this is just a linear combination of the random variable x, right? So one can show, or one should be able to show up to this point, if x is a normal random variable, then that means z will also be a normal random variable, because as we should already know, a linear combination of normal random variables will also be a normal random variable. Of course, the mean and the variance of that normal random variable z will be different, but nonetheless it will be a bell curve shape distribution. So let's see if we can find a formula for the mean and the variance of this random variable z, okay? So what is the expected value of z? Because that's another way of saying the mean of z. So that's going to be equal to the expected value of 1 divided by sigma x times x minus mu x all over sigma x. So keep in mind x is just a variable and we can distribute expected values over this expression. So we're just going to be left with 1 over sigma x times the expected value of x minus the expected value of a constant is just that constant, and that's the expression we have. So what is the expected value of x? So the expected value of x is just going to be mu x, so we're going to have mu x there, minus mu x divided by sigma x. Now keep in mind that that expression and that expression are equivalent, so when we subtract them off, we get 0. Notice it doesn't really matter what the mean of the distribution x is, the expected value of this z-score will always be equal to 0. And that's an interesting property. So what about the variance of this random variable z? So let's look at that. So the variance of z is going to be equal to the variance of that expression, so 1 over sigma x times x minus mu x all over sigma x. And we can distribute variance over a single variable with no big issue, and keep in mind that the variance of a constant is just equal to 0, and when we factor this constant out, it will become square. So this is going to be equal to 1 over sigma x squared times the variance of x plus 0. I'm just going to write it there just for clarity. And what is the variance of x? Well, the variance of x, we know, is just going to be equal to sigma x squared, and notice that regardless of what sigma x squared is, as long as it's not 0 or infinite, these will cancel and we're going to be left with 1. So that means if x is a random variable, any random variable, doesn't have to be normal, doesn't have to be exponential, it can be anything you want. The z-score random variable of that original random variable will always have an expected value of 0, and the variance of a z-score will always be equal to 1. And those are very, very important distributions. All right. So if that is the case, that means if x is normal, then that means the distribution of x is going to have the formula 1 over sigma times the square root of 2 pi times e to the minus 1/2 x minus mu divided by sigma, the quantity squared, right? But if x is normal, that means that zx is also normal, with the mean being equal to 0 and the variance to be equal to 1. And if the variance is 1, that means the standard deviation is also equal to 1 because it cannot be negative. That means the distribution of the z-score for x, so the distribution of z, is going to be equal to, if sigma is equal to 1, we're just left with 1 divided by the square root of 2 pi. And then we're times e to the minus 1/2. Sigma is 1, mu is 0, so we're just going to be left with x squared. So it's a very nice compact representation of the probability density function for a normal distribution. So this distribution is what we refer to as the standard normal distribution, as you should already be familiar with, especially if you're familiar working with like z-tables and stuff. But we're actually going to give this a new name. This is going to be called the z distribution, i.e. the first of the 4 special distributions that we're going to be calculating with. Now, what is the purpose of the z distribution? So keep in mind, even though we do not necessarily know what the mean and the sigma of a distribution are, we could always find the distribution of the z-scores as long as we know that the original distribution is normal. Therefore, we can always use distributions on the z-scores even though we do not know the domain parameters, okay? So importantly, z will help us make inferences on the distribution of the sample mean if the sigma standard deviation of the population is known. I'm not going to get into the details of what I mean by this statement and the applications of it, just keep it in mind just for the time being. The next concept that I want to introduce that is going to be very related to both the z, t, chi-square, and f distributions is what we refer to as critical values. Critical values are going to play a very important and pivotal role once we start talking about hypothesis testing, both for what we're going to call confidence intervals, test statistics, and p-values. So in this video, I just want to talk about sort of how to calculate critical values, and then later we can talk about the applications and the purpose of what these critical values are actually going to do. So a critical critical value, in short, is just a cutoff point associated to some theoretical distribution. For example, that theoretical distribution could be a z, t, chi-square f, binomial, exponential, any distribution whatsoever can have critical values, for which a predefined or desired area or probability is associated to that particular cutoff point. Okay, so what I want to do is actually look at, for example, the z distribution. So we know the z distribution is going to be a Gaussian, and it's going to be looking like this. And let's assume we want to find a value here, and I'm going to call this value c sub cl. So ZCL, this is going to be like Z critical L for left, and I'll talk about why I'm going to call it left in a moment. And what I want this point to be associated to is a point such that to the area to the right of it is going to be equal to 1 minus alpha, and to the left of that particular value is going to be alpha. Okay? So for example, if I say let alpha be equal to 5%, what is the value ZCL that is going to be associated to that alpha value where this picture is associated to, say, a Z distribution? So every time you have a picture like that where you want your alpha to be in the left tail, this is usually what we refer to as a left tail critical value. Okay. Similarly, we're going to have two other pictures that are going to be very important to us. So let's assume we have that picture. So what if we do not want the alpha to be in the left tail? Let's assume we want the alpha to be here. And let's assume that we want 1 minus alpha to be here. Right? And eventually we're also going to call 1 minus alpha to be equal to c. That's going to correspond to our level of confidence. So if we have that point in the right-hand side, we're going to be abbreviating that by z critical right? And this is going to be associated or called a right tail critical value. And then we're going to have another picture. Let us assume that we want the alpha to be equally distributed in both of the tails. And if it's symmetrically distributed, that means alpha over 2 is going to be in the left, alpha over 2 is going to be in the right, and although this picture does not look symmetric, let's pretend that that is 1 minus alpha, or c. So if that is the case, that means we're going to have two critical values. This is going to be equal to ZCL and ZCR, and this is what we call a two-tail critical values. Now, although this picture does not look symmetric, that's actually a good thing, but usually when we talk about two-tailed tests, we're usually talking about symmetric cases. It's not necessary that these tails be equally weighted. For example, that could be alpha over 3, and that could be, for example, 2/3 alpha or 2 alpha over 3, such that the total of those tails is equal to 1. That would be called an asymmetric two-tailed test. We're not going to be talking about two-tailed tests, at least in the near future, but for now, keep in mind the tails do not need to be equally weighted. So now, let's get into the problem of how to actually solve these problems or find these critical values for some desired level of alpha, because alpha can be anything between 0 and 1. Okay, so keep in mind most problems for normal and also z, chi-square, and f you cannot solve by hand. You have to use software. So I'm going to be giving the formulas using Excel on how to calculate critical values. So let's assume we want our alpha value to be equal to 7.3%. or 0.073. And let's assume that we want to calculate the left critical value. So ZCL, where alpha is located there, right? So obviously, since alpha is less than 50%, this ZCL value should be equal to a negative number, and one should be able to find that this is approximately equal to negative 1.4538. So how to generate this number in Excel? In Excel, you can use the function norm.s.inv. So norm stands for normal, S stands for standard, so standard normal, and INV just means we're doing an inverse problem. That is, I'm giving you a probability, you're giving me a domain value instead of me giving you a domain value and you giving me a probability. So we're sort of working backwards. So that's going to be equal to norm.s.inv of the alpha value you're associated to, and make sure that that is a number between 0 and 1. Now let's look at the other value. Let's assume that we want a right critical value, so ZCR. Right? So let's assume that we want that alpha value to be over there. So what is that value going to be equal to? So you should be able to find that's approximately equal to 1.4538. Notice that these 2 points are symmetric to each other. That shouldn't be surprising because if alpha is over there, its mirror image is going to be over there and it's going to have the same value, just opposite sign. But not all distributions are symmetric, so you need to have a formula that sort of calculates it even for the asymmetric case. So in Excel, that's going to be equal to norm.s.inv. So norm.s.inv of, now this norm.s.inv function calculates all areas to the left of the critical value for which you're interested in. So if alpha is to the right, that means the area shaded in green is going to be 1 minus alpha. So norm.s.inv of 1 minus alpha will generate this value ZCR. And typically this alpha value, if it's between 0 and 50%, will always produce a positive value. Now let us look at our two-tailed test. So let's assume this is our distribution. So let's assume we have that point there and that point there. So if our alpha is symmetrically distributed within the tails, that means this area all over here is going to be alpha over 2, and that's going to be alpha over 2 as well, with 1 minus alpha on the interior. So we're going to have two numbers here. So we're going to have ZCL and ZCR. One should be able to find that this is going to be approximately equal to negative 1.7928, and take a guess at what ZCR will be equal to. That's going to be positive 1.7928 due to symmetry. So in order to calculate this ZCL value, let's use the same exact colors here just to stay uniform. You could use norm.s.inv of, so what's the area to the left of ZCL? That's going to be alpha over 2. And for this value, that's going to be equal to norm.s.inv. And what's the area to the left of ZCR? That's going to be 1 minus the area to the right of it. So 1 minus alpha over 2 for that right critical value for the Z distribution. So that is how you can calculate critical values associated to a Z, or standard normal distribution. For the next distribution, let us start by defining a sequence of independent and identically distributed normal random variables. That is, z1, z2 down to zn are all normal random variables with the same exact mean and the same exact variance. You can sort of think of this as, for example, the amount of sleep that you and your friends have, let's assume, are all normally distributed with the same exact mean and variance. But the amount of sleep that each of you will get possibly will be different at different times. So hence Z1, Z2 down to Zn are the distributions of each of your sleep cycles or sleep amounts, let's say. So what we're going to do is we're going to define a new random variable. We're going to call this variable c, and this is going to be equal to the sum of the squares of each of these variables. So z1 squared plus z2 squared all the way out to zn squared. So obviously this random variable is always going to be non-negative, provided that these values only take real number values, which typically is what we're going to be filing. So one can show that this variable c will follow not a normal distribution, because normal distributions can be negative. So we'll follow a non-negative distribution, and this distribution is called a chi-square n distribution. A chi-square n distribution. So this chi-square n distribution talks about chi-squared random variables. So a chi-square random variable, so a chi-square, which we usually represent as chi-square n random variable, is one that follows a chi-square distribution with n degrees of freedom. With n degrees of freedom. Okay, so let's just look at the distribution of this just in case you were curious. So the distribution of this random variable c is going to be equal to 1 divided by 2 to the power n divided by 2 times gamma of n divided by 2 times x to the n divided by 2 minus 1 times e to the minus x over 2. So if you were to graph this, say in Desmos, you're going to have a graph that looks sort of like that, where it's starting at 0 and goes up to positive infinity. All right? And just in case you learned about the gamma distribution, this is actually a special case of the gamma probability density function with our rate parameter lambda to be equal to a half and the number of exponential random variables to be equal to n minus 2. All right. Now there is a theoretical property that the chi-square random variable has, and this is called Cochran's theorem. I'm not going to go through the proof of this or its applications, so let's just take it as fact for now. And it says that if we define the variable c to be equal to the sum from k is equal to 1 to n of zk minus the average of zk squared. So what is this? Well, that's just a sum of squared differences for that random variable. Now, if z is a standard normal random variable, we know that z bar will be equal to 0, but we're not assuming that z is standard normal, we're just assuming that z is normal. So one can prove that this random variable zk minus z squared, i.e. the sum of squared differences of that normal random variable, will be associated to a chi-squared distribution with n minus 1 degrees of freedom. So that means this sum of squared differences will be a chi-square n minus 1 random variable. And this is going to help us make inferences, for example, about variances. Right? So let's actually just state that just to be formal. So chi-square n minus 1 will help us make inferences about the sum of squared differences and hence make inferences about what? So what other metrics are very closely related to the sum of squared differences? That would be the variance and also the standard deviation, right? But important in start, it's just going to be the variance of a random variable, in particular a variance of a normal random variable. All right, so now let's talk about how to calculate critical values. So critical values, let's assume we let alpha be equal to 8.3%. And let's assume our degrees of freedom, let's call that V, is going to be equal to 14. That means we're going to be calculating things with respect to a chi-square 14 distribution. Each degrees of freedom is going to have a different chi-squared. So if you change the value of V, you will change your distribution and hence the critical values associated to them. All right, so let's draw our first picture. So let's assume that we want our alpha to be equal to that little region, so the left tail. So I'm going to call this number a chi-square critical value on the left. One should be able to show that that's approximately equal to 7.4269. So how do you calculate this in Excel? That's going to be equal to CHISQ dot INV, so it's an inverse problem still, but for the chi-square distribution of alpha, comma, the degrees of freedom. Similarly, let's again draw our little chi-square distribution. Let's assume that instead we want our alpha to be in the right tail. So how would we calculate that chi-square CR value? So one should be able to show that that's 21.7916. How do you calculate it in Excel? That's going to be equal to CHISQ.IMV, the area to the left of that number, which is going to be 1 minus alpha. And let's draw our last picture, so our two-tailed distribution. So let's assume that we want our alpha equally distributed between the lower tail and the upper tail, meaning that that's alpha over 2, that's alpha over 2, and the area to the left is going to be 1 minus alpha over 2. Right? So we're going to have two critical values here. We're going to have chi-square CL and chi-square CR. Right? So one should be able to show that that's approximately equal to 6.2950, and that's approximately equal to 24.3546. So that's how you calculate your left tail, right tail, and your two-tailed critical values for a chi-square distribution. Very important though, notice that these chi-squared values for the two-tailed test are not symmetric. So even though you can get away with only calculating one for the z distribution, you have to calculate both the left and the right critical values for a two-tailed chi-square test, which we're definitely going to look at applications a little bit later. Both the z and the chi-square distribution are both related to the variance of a normally distributed population. But what if we don't know sigma? More so, what if we do not know sigma squared? So keep in mind, we have already proven that the expected value of the sample variance, i.e. the expected value of 1 divided by n minus 1 times the sum from k is equal to 1 to n of xk minus x bar the quantity squared actually is equal to sigma squared, i.e. 1 divided by capital M times the sum from k is equal to 1 to n of xk minus mu the quantity squared. So what does that exactly mean? That means that s squared is an unbiased estimator of sigma squared. Now, I want you to pay attention to one very important thing. Notice that that is a number, that is a random variable. Okay? That is a very, very important thing to note. Now, how are we going to sort of bring this in, and how does that relate to these special distributions? So remember, for the z distribution, the z-score for a random variable x was equal to capital X minus mu x divided by sigma x. But what if we do not know what x is? Well, also keep in mind that we can actually rewrite this in terms of the z-score for the sample mean. So if we're interested in the z-score for the sample mean, that's just going to be equal to the sample mean minus the mean of the sample mean divided by the standard deviation of the sample mean. Now, we've already proven at the beginning of this discussion that mu x bar was the same as mu x, and sigma x bar was the same as sigma x divided by the square root of m. So that means the z-score for the sample mean is actually just going to be equal to x bar minus mu x divided by sigma x divided by the square root of m, which some people would sometimes prefer to write as just the square root of n times x bar minus mu x, all divided by sigma x. Now again, what if we do not know what sigma x is equal to? Well, if sigma x squared can be approximated with s squared, maybe we can just approximate sigma x with the sample standard deviation. So we're going to define a new random variable. I'm going to call this t. This is going to be equal to the square root of m times x bar minus mu, all divided by capital S, right? Now, note here, square root of n is the square root of the sample size. That's just a number. Mu is the population mean. That's just a number. But x bar, this is a random variable because it depends on the sample. And s, the sample standard deviation, is also a random variable because it depends on the sample as well. So what are we sort of defining here? So notice that this is almost like we're doing, let's write it like this, that's the square root of n times x bar minus mu divided by the square root of s squared. Right? Now remember, if we assume that x bar is a normal random variable, if x bar is a normal random variable, that means s squared, which is sort of related to the chi-square distribution, is going to be associated to just a chi random variable, or the square root of a chi-squared random variable. So what do you get when you divide a normal random variable by a chi random variable? You get a new random variable, which is called a t random variable, which is going to have some level of degrees of freedom, right? Which I'm going to call v just for short. Now, what is the distribution of this random variable? Let's give the formal probability density function representation for t. So f of t is going to be equal to gamma of v plus 1 divided by 2 divided by the square root of v pi times the gamma of v over 2 times 1 plus x squared divided by v to the power negative 1/2 times parentheses v plus 1 in the exponent. So if you take a look at this distribution, say in Desmos, you're going to have a distribution that sort of looks like this. Actually, that's a horrible graph of what this distribution looks like. It actually looks more like that. So one can show that the mean of this is equal to 0, but it's going to have wider tails than the normal distribution does. Okay, so that's one subtle difference that the t distribution has compared to the normal. Also keep in mind, different degrees of freedom gives you different distributions of t, but nonetheless they are all probability density functions. There's a very important theorem that actually connects the standard normal and the t distribution, and it is this particular theorem. if you make the degrees of freedom arbitrarily large for the TVX distribution, you're actually going to get a Z distribution, right? So this is actually one of the origins of the n bigger than or equal to 30 rule. Because if our degrees of freedom, which is typically taken to be the sample size minus 1, is arbitrarily large, you can actually approximate the t distribution with the z distribution. So when n is bigger than or equal to 30, a lot of the t critical values are actually close to the z critical values, up to say about 2 decimal places. But if you want more accuracy, you definitely need a sample size larger than 30. But typically speaking, even if n is 50 million, this will still follow a t distribution if you do not know sigma, right? So I just want to make that point very, very clear. So even if our sample size is very, very large, even if n is bigger than 30, because a lot of people still follow this procedure, the variable t, which is equal to the square root of n times x bar minus mu over s, will still follow a TV distribution. It just will be approximately a z distribution. So you're going to be adding error if you use a z distribution, and some people are okay with that, but that's for them to decide. All right. So let's look at how to calculate critical values in Excel for the t distribution. So let's choose alpha to be equal to, let's go with 10.2%, so 0.102, and let's assume we're working with the degrees of freedom equal to 21. So we're going to have 3 different pictures as usual. So we're going to have a nice little symmetric distribution. Let's first off start off with our alpha to be in the left-hand tail. So we're going to have a left critical value for t. One should be able to show that that's approximately equal to negative 1.3110. Then we're going to have our right tail critical value, where alpha is in the right tail, so ZTCR. One can also show that the t distribution is symmetric, so that means that's going to also be equal to 1.3110. And then we're going to have our two-tailed critical values, right? And let's assume that this is a symmetric two-tailed critical value with alpha over 2 on the left, alpha over 2 on the right, and 1 minus alpha over 2 to the left of the right one. So we're going to have TCL and TCR. One can show that TCL is approximately equal to negative 1.7100, and that's approximately equal to positive 1.7100. Right? In Excel, how am I generating these values? So you can use equals t.imv, so t.imv, what's that dot doing there, of alpha, comma, v, or nu, depends how you read that letter. This is going to be equal to t.imv of 1 minus alpha, comma, nu. The left critical value for the two-tailed test, that's going to be equal to t.imv of alpha over 2, comma, nu. And the right one, that's going to be equal to t.imv of 1 minus alpha over 2, comma, v. And that's how you can calculate critical values for the t distribution. Now let us start to take a look at the last distribution of today, and that is the f distribution. So the z distribution is going to be helping us make inferences about the population mean if sigma is known. The t distribution is going to be helping us make inferences about the population mean if sigma is not known. One can also show that the z and t distribution is going to help us compare two different population means to one another. The chi-square distribution is going to be helping us make inferences on the population variance. And lastly, the f distribution is going to be helping us make comparison tests about two population variances. But instead of subtracting, we're going to be dividing for the f distribution. Because remember, if you have two population variances and you subtract them, that difference could be negative. And that's not good because generally variances can't be negative too. But when you divide two non-negative quantities, you're also going to get a non-negative quantity, which motivates the creation of this f random variable. So take a note that this chi-squared variable on top is sort of like a sum of square differences. And if we divide by, say, n minus 1, then on the top is practically like a variance of a sample or a variance of a population. Similarly, on the bottom, we have a chi-square random variable, which is like a sum of square differences for another sample, possibly of different size. And then we're going to be dividing by that sample size, say, minus 1. So we're sort of dividing two sample or population variances to one another. So what does the distribution of this random variable look like? It actually has a very similar shape to the chi-squared variable, but it's a little bit more flat, and the domain variables typically are going to be a little bit more smaller. Once we start talking about applications of the F distribution, which there are so many applications of it, it's probably one of the more important of the four. You're going to see that all of the values are sort of going to be floating around an F value of 1. All right, so let's first off just state the analytical distribution for the F distribution, just in case you're interested in analyzing it, say, in analytical software. So this is going to be equal to gamma of degrees of freedom 1 divided by 2, gamma degrees of freedom 2 divided by 2, all divided by gamma of the sum of those fractions, v1 over 2, v2 over 2, times 1 over x, so clearly x cannot be equal to 0, times the square root of v1x times v1 times v2 to the power of v2, all over v1x plus v2 to the power of v1 plus v2. Although x cannot be equal to 0 for this term, if you plug in 0 into the top, you're going to get 0 over 0, and you can actually show that the limit as x approaches 0 from the right is equal to 0. So 0, at least in the limit term, is just equal to 0 in this particular case. All right, so that's the PDF, and that's how you can generate it. But keep in mind, this F distribution is going to have 2 degrees of freedom. A degrees of freedom for the top, and a degrees of freedom for the bottom. So it's going to have a degrees of freedom pair, v1 comma v2. Now, a nice little analytical property that's going to sort of come up in a couple applications is the following two theorems. If f is associated to an f(v1, v2) distribution, then the reciprocal of that random variable, because if we're dividing two variances, one can answer, well, does it really matter the direction for which we divide them? Can we do variance 1 over 2, or should we do variance 2 over 1? Well, the reciprocal of that variable is actually going to be associated to an f(v2, v1) distribution, and that's a very nice theorem to keep in mind. Now, a very interesting connection between the F distribution and the T distribution is the following. If you have a T random variable with V degrees of freedom and you square that random variable, you're actually going to get an F distribution with a degrees of freedom pair 1 comma V. Now, this is a very, very interesting and on the surface weird property because it connects two random variables together in a very strange way. But later, when we start talking about a little bit more advanced methods, this is actually going to become very, very obvious of why it actually is the case. So now we have the analytical properties discussed of the F distribution. Let's just go ahead and calculate critical values associated to an F distribution. All right. So let us assume that we're working with an alpha value of 3.24%, so 0.324. Let's assume the degrees of freedom for the top is equal to 32, and the degrees of freedom for the bottom is equal to 18. Keep in mind, if you do reverse these degrees of freedom, you will get different answers for your critical values. So make sure you have the order in the correct way. All right, so we're going to have three pictures as usual. So let's assume first off that we have alpha in the left tail. So we're going to have a left critical value for the left F distribution. One can find that's approximately equal to 0.4757. Similarly, if you want to calculate a right tail distribution, it's not symmetric, so you have to calculate both, right? So let's assume we're over here. Let's assume that's our alpha value. So that's going to be our FCR critical value. One can show that's approximately equal to 2.3031. Notice that CR values are sort of floating around x is equal to 1. That's typically normal for an F distribution. And if we want our two-tailed F distribution, our symmetric two-tailed F distribution, that is, we want alpha over 2 in the left, alpha over 2 in the right, so we're going to have an FCL, and an FCR, critical value, we're going to have that's approximately equal to 0.4223 and 2.6470. Now, how do you calculate these in Excel? This is going to be equal to f dot inv of alpha v1 comma v2, and then the right critical value is going to be f dot inv of 1 minus alpha v1 comma v2. And then for each of these, our two-tailed left and right critical values, that's going to be equal to f dot inv. So f dot inv alpha over 2 v1 comma v2. And then this is going to be equal to f dot inv of 1 minus alpha over 2 v1 comma v2. Right? So those are the z, t, chi-square, and f distributions, some theoretical properties, some insight on the applications they are going to be used for, and how to calculate their left tail, right tail, and two-tail symmetric critical values for each of the distributions in Excel. So later we're going to get into the applications once we start talking about hypothesis testing, but for now those are just the basics of the z, t, chi-square, and f distributions. So until next time, I hope you take care. See you.